All right, welcome back. We are Game 3001. That's Artificial Intelligence for Games in the winter 2022 semester at George Brown. And it's week 10, part one of our broadcast and recording in time together. So this is our lecture recording. And today we're talking about state machines, which is an alternative method to making good decisions for autonomous agents. Let's talk about what those things are. So again, last week we talked about decision making in general. What is decision making for AI? We talked about a single method to do that. Kind of the first method was decision trees, which I always felt was a good method because it's fast, it's simple to implement, as an example, and it gives us an idea of how to make decisions based on a tree-like structure, yes, no kind of answers. Very, very straightforward. Maybe not as realistic and not as complex, let's say, as some other methods that we also mentioned. And we also started Lab 6. Again, Lab 6, just to let you guys know, is the completed lab is now due this week, Sunday. So not next Sunday, it's actually this Sunday at midnight. And that's what this says too. Lab 6, Part 1 and Part 2 due Sunday at midnight. This week we're talking about state machines. One thing to note is that all things being equal, that means if everything is the way it is, then next week is when assignment 3 is due. Please, if you haven't had a chance to do so already, please sign up for groups for assignment 3. So that's A3 groups for A3 and A4 groups for assignment 4. If you're planning on doing the assignment 3 and 4 with the same group of people, you can sign up for both already. It's available to you. But the reason why we gave this ability is for you, if you're not happy with the group, you can always switch to something else, and you need a good assignment 3 as a base. That is a requirement for assignment 4. So that's what we talked about already. So state machines is what we're talking about today. And we're sitting here at week 10. Next week, which is very interesting, again, one of my favorite topics is behavior trees. So kind of extending the idea of decision trees to the next level, where we have a bunch of different kinds of decisions that can be made. Lab 7, when we started off next week, we'll be talking about the tree node class, and we'll be extending the stuff that we've given you, this week and last week, in order for us to help you to build assignment 4. Okay, so that's where we're going with the stuff we're doing next week. So let's talk about then what state machines are. So really what we wanted to think about is that, we want autonomous characters to act in some kind of way. They will make decisions, as an example. And we talked about decision trees, and we also talked about random decision trees. So that way it's not always the same kind of response or decision that will be made by a autonomous agent, because if we have the same response every single time, what ends up happening is you have a predictable AI system, which could break the immersion, reduce your suspension of disbelief when it comes to playing a game. That's not really a great thing to have. And we've seen and we've talked about how if you're always dealing, even if it's a great AI, but it's very, as an example, predictable, then it becomes a bad AI. It doesn't matter. Okay. So a lot of times, what we use is something called state machines. State machines is a little bit even easier to implement, maybe not as fast and maybe not as detailed, let's say in some ways, as decision trees, but state machines are pretty good in terms of the way they deal with decisions as well. So again, it's one of the most often used decision-making algorithms or programming patterns that we use. And it comes from the state pattern, the state programming pattern, which is one of the 23 design patterns that we keep talking about that were kind of designed back in, or documented back in the 90s, 1990s. So, so what they do is they take into account the world state, the state of the world, and similar to decision trees. Remember decision trees we talked about, there's an external state and there's an internal state. And it's kind of the same thing with state machines. State machines have both an external state and an internal state. Okay, they use both of those types of informations. So really, when we think about a state machine, autonomous characters or agents, let's call them agents, they always occupy only one state, and there's normally some kind of actions or behaviors associated with each state. So we'll talk about what those are in a second. So as long as the autonomous character remains in that same state, it will continue carrying out the same action. An example of this would be if I'm in the patrol state, then if I'm the autonomous agent, then I'm going to keep wandering around and patrolling. And if I see the player, line of sight, sensing radius, or whatever, then it will make me transition. So this is the transition, which is a connection from one state to another state. It'll make me transition from the patrol state to something else, another state. Maybe it'll be move to if I have a loadout that is more of a melee type of enemy type, maybe I'll move closer to the player if I was the autonomous agent. If I'm a ranged attack type of loadout, then I'm going to probably just get to a station keeping post and start firing bullets or whatever weapon I can at the player, right, as an example. Or maybe I'm a different kind of agent altogether where I'm patrolling, but so I raise the alarm. That could be another state. I go to the raise the alarm state, where I go to the nearest alarm station and then I pull the lever and then there we go. Everyone knows that the player is here, kind of thing. Is attacking our base or whatever. So that's the way we have a state, and then we can transition from one state to the other state. And really what happens is when we transition because of some kind of condition that has been met, whatever that condition is. Example would be, I have a line of sight, or we've seen the player, or we've heard the player, or the player has entered a specific. They kind of went into an area where they triggered an alarm somehow, right? So something that was automatic. We didn't see them, we didn't hear them, but they triggered an alarm because they passed through this kind of a trap or something like that triggered the alarm. When the transitions conditions are met, we say that they trigger the change, and when the transition is followed to a new state, it has fired. The transition is fired. Okay, so it's been triggered, and after it's been triggered, after it's done, transitioning gets fired. It's gone to the new state. This is just keywords that we can use to talk about them. State machines have 4 different components, and the first thing is about actions. So they can some kind of behavior that they produce, which is the action itself. Okay, so that's the first thing. The second thing is some kind of transition. So almost like a connecting line between the current state that they're in and other connected states, other things that they can go to, right? And third thing is some kind of rules or conditions that allow us to change state. If I'm in a specific state that I'm in right now, again, example, I'm in patrol state. What are the conditions that are going to transition me from patrol state to an attack state, let's say, as an example. And the other thing is some kind of events, input events, which are either externally or internally generated, which may possibly trigger rules and lead to state transitions. So when we trigger rules, inputs would be things like the player moving into a certain spot, the player moving into line of sight. Those are inputs that trigger the rules. Okay, so those are the 4 things that state machines are made from. State machines, again, have an initial state where they're starting off. Example would be patrol state. That might be the initial state of a state machine. Think about this as the AI brain for an autonomous agent. They have an initial state. And then they're going to have a current state, as an example, where that they're in right now. So they had an initial state, but now they're in a current state. Those things could be the same things. Initial state and current state might be equal, or initial state and current state might not be equal if they've moved away from their initial default state of patrol to something else like attack. Okay, so current state remembers the product of the last state transition, which is important. Where did we come from? So a lot of times we want to know that as well. So here's an example with a state machine with 3 states. Okay, so example, the little circle, a black dot, if you will, with this arrow. This is kind of a diagram that basically tells us that we're starting here and the starting state is on guard. Okay, now there are only two transitions that could be made. Okay, just to show you this, if we're going to read the diagram together, there's two transitions that can be made that goes from the on guard state. The other one is this one here, which is a really ugly color. Let's make that a red color. And let's also make the line a little thicker. So let's suppose I'm from here to here. That is the first, connected line. The other connected line is from here to here. Okay, so those are the two connected lines. And notice that they are directed arrows, which means just like before, when it looks like these nodes, there's only two ways of getting out of this position, similar to what we did with decision trees. Okay, so you can only go to fight or to run away. All right, and when we think about that, those are the transition that we have. Those are the connected lines between this current state, which is on guard, to one of the other states, which is fight or run away. So those are the three different states here. So the condition is this one right here. So this is the condition. If we see a small enemy, we're going to go fight. If we see a big enemy, and a big enemy might be someone who has more health, as an example, or just generally stronger, maybe the guard can detect how big that enemy is, then we do different things. Okay, so this is the condition, and we transition. The line that connects the two states is the transition between one state and the other state. So let's say, for example, I'm on guard and I see a small enemy. So I have line of sight with a small enemy. I move to this new state, fight. So I'm fighting the enemy. Maybe if I'm a guard that's a close combat guard, I'm going to move to fighting position and fight with him. If I'm losing the fight, so if I'm somehow losing, I'm having less than half hit points, as an example, then I'm going to transition from fight to run away, because I'm going to kind of take care of my self-preservation goal and run away. Right? And if I run away far enough, the only transition that I can go from run away is I've escaped and I can go back to guard. Right? So it's weird. It's not exactly great. Well, because what if I go back to guard, but I really haven't escaped? The character is still there. It doesn't say anything about healing. It doesn't say anything about anything, right? So I'll just maintain my health and just go back to guarding again, which is not a very smart thing to do. We could think about other things that this AI could do as well. But the idea here is very simple. The states are on guard, fight, or run away. And again, each state has one or more transitions. Okay, so again, transitions from on guard are either to fight or to run away. Transitions for fight is only one. If we're losing the fight, we run away. And transition from run away, there's only one. We go back to on guard. Again, a very simple state machine. Questions around this before we move on? So only three states that we're talking about so far. So one thing I love about state machines is that they're super simplistic, all right, in terms of like the options that you have. If it's not connected, you can't go there, right? One thing to note is that you can have multiple connections for a state machine, right? Not just two. So in other words, it's not a binary connection. It could be three or more, right? And you also know about your previous state, where you came from. All right, so again, we just talked about this this diagram. We're using UML, which is Unified Modeling Language. States are shown as curved boxes. Transitions are arrow lines, and then conditions are contained in square brackets. Solid circle is the starting state, initial state. All right, so really then, in a decision tree, the same set of decisions is always used, right, every single time. And any action can be reached at any time through the tree. In a state machine, only transitions from the current state are considered. So not every action can be reached at any particular time, only the current state and its neighbors. So a good example of that is, let's suppose I'm in a wander state. What can I do when I'm wandering around? This is kind of like patrolling, right? I only have one possible condition to move me from out of this state, right? Which is if the player is near. So the player is near. It could be line of sight. It could be sensing radius. If the player is near, I move to attack, right? I'm in my attack state. Now there's two lines that go from attack. I could move here as an example, or I could move there. So if the player is out of sight, I go back to wandering. Again, I'm not sure this is a great scenario because it doesn't make our AI too smart. Or if I'm attacking, as an example, then if the player is attacking back, then I go back to evading. So I kind of try to dodge out of the way so that I'm not going to attack when they're dodging. What happens when the player is not attacking? Then I attack, right? If the player is idle, then I go back to attack. So if they don't attack me back. Again, you can define these conditions differently, right? If I'm here, I'm evading, and the only place I can go from evading is either back to attack, or I can go over to health points are low. I can transition to first aid, right? Which means go get, find first aid. If I've found first aid and I've healed myself, then I go back to wandering. So there's no way of going back to attack the player again, which again is a very simple example of a state machine, some decisions that are being made. All right, so one thing we talk about when we talk about state machines is oftentimes we call them finite state machines. All right, so so that's this data structure that we're creating, and we're going to talk about what those are. And sometimes finite state machines, or FSMs, are the things we talk about when we're using state machines for decision making. FSMs, finite state machine. So really, an FSM in computer science normally refers to some kind of algorithm used for parsing text. So I have some kind of condition as an example that I'm looking through, and then I'm going to use a parsing method or a branching method to go from one type of can move from one type of state to another state. So here's an example of a switch case. Switch cases are what we use a lot of times with state machines. We have already seen switch cases in our little framework that we've kind of put together, the SDL framework, which basically allows us to move from one scene to the next scene. Switching scenes is moving to a different state. We're moving from one scene state to another scene state. And you guys have done state machines in your fundamentals as well, but we're just going over some of this as well right here. So again, let's suppose we have a game mode that is an enumeration, and the enumeration would be 0, 1, 2, 3. It represents numbers, typically in C++. Then if my game mode is paused, then player can move is equal to false, enemies can move is equal to false, spawn new enemies is equal to false, time scale is equal to 0. All right, so that's how the pause mode works. If we're in the active state, then the player can move, the enemies can move, spawn new enemies are true, and the time scale goes back to 1, so things are moving again. If I'm in the game over state, the player can't move, the enemies can't spawn, but enemies can move around. Why not, right? So we can show the enemies, and the time scale is 1. So again, very straightforward way of switching from one type of play state to the next. And this would be like different kinds of game states, if you will, paused, active, or game over. All right, very simple way of doing it, and that's your finite state machine. So when we talk about the game finite state machine, or game FSM, right, really what we're saying is that there are, we want to be able to implement the finite state machine in a certain way, but everyone has a different technique on how to do this. So one of the things is it's difficult to kind of show a single algorithm for this thing, because at the end of the day, programmers can write this thing in many different ways, right? Let's talk about the problem that we're trying to solve. So we would like some kind of general system that supports arbitrary state machines with any kind of transition conditions. I want to move from one state to the other state with any kind of condition that I want. So a general state machine is what I'm looking for, right? And the state machine will conform to the structure given above. So it's going to have those 4 properties, and it's also going to have an internal state and or an initial state and a current state, those things that we want. And it'll only occupy one state at a time. So it can't have multiple states happening at the same time, okay? Each state machine. So really the algorithm, when we think about it, is this: we're going to use something called a generic state interface that can be implemented in the code. What we want to think about is we're going to have a set of possible states, how many states there are. A lot of times what I would do with this is use some kind of enumeration, right? An enum. right? So again, what state I'm moving from one state to the other state, attack state, pursue state, flee state. Those are all different kinds of states that we can have for the AI, right? So again, determining their actions. Again, states are very linked to their actions. Okay, that's what they are. And alongside each state, we have a series of transitions. So from the flee state, what can I do? What are the things that I can do from a flee state when I'm fleeing? Can I get aid? Can I heal? Or can I leave? Do I leave the game? If I'm leaving the game, then do I reset? Do I come back as another character? Do I go back to the game object or the object pool? What do I do? And so that's a set of possible states. What if I'm attacking? What states are there when I'm attacking? Can I have, when I'm in attack state, what can kick me out of attack state? If I'm dying, is that something that can kick me out of attack state? What if I'm winning? What do I do then? Do I do crazy different kinds of attacks when I'm winning? So I have different kinds of attacks. I have maybe a basic attack, and then when I'm really great doing well and I have a lot of health compared to the player, maybe I'm going to try something riskier and try and do like some kind of sweeping attack or a spinning attack or something else if I'm doing a melee attack with the player, right? So some kind of possible states that I can be, and different transitions between states. Each transition is, again, using a generic interface, which we're going to be talking about. And it really simply reports back to the state machine whether it is triggered or not. So that is the transition. Okay, so that's what this is. And the great thing is, when it comes to keeping this all straight, it's pretty straightforward in terms of how it's going to work. We can picture it. This is the thing about state machines; they're very intuitive in terms of how we can put them together. So at each iteration, think about this as every frame. As an example, the state machine's update function is called. That update function is going to be linked to, let's say, the scene's update function, just like we do with a lot of our game objects today. And then, and what we do is we check to see if any transition from the current state has been triggered. So did we trigger a state change? If the state change has been triggered, then, and it's, let's say a transition is scheduled to fire, then we wait for the next frame in order for that to happen, typically. Okay, so then the method compiles a list of actions to perform from the current active state. Sometimes there's another transition action that's going to happen. A good example of that is if I'm transitioning from, let's say, attack to flee, maybe what I'm going to do is I'm going to have an animation while I'm transitioning that, basically puts my weapons away while I run. Or I drop my weapons and run. It's different ways of doing things. So you can trigger a certain amount of other kinds of actions at the same time. Okay, just going to move on from here. So this is kind of what I'm just going to move in just really briefly just to kind of talk about some pseudocode a little bit. So again, we talked about initial state and current state, right? Where when we initialize the first time, we say that the current state is equal to the initial state when we first start off, right? We have some kind of public update function which returns an action array. So this is an action array, something that I'm going to, one or more actions that I'm going to be performing, right? When we start off in the update function, we haven't triggered a transition yet. So we start off with the triggered object be returning null. We don't have anything that it's returning. We set it to null. It is a type of transition that we're going to call. Okay, and then what we're going to do is for every transition, for each transition that we have in the current state machine, all right, we want to get those transitions. So remember, if we're going to go back to that previous example, we're going to have one or more connections. Remember, transitions are connections between one state and another state. If the transition is triggered, so if that transition is true, right, and those transitions are going to be triggered based on conditions, right, whatever the conditions are, then the triggered variable is equal to the new transition that is triggered, whatever that is, okay? And as soon as we have a transition that is triggered, we break out of this loop. So we look through each connection and check to see if the condition is met. That's really what we're doing, okay? If we have a transition that is triggered, the transition or the triggered variable points to the transition that's been triggered. And what we want is the new target state where we're going to is the triggered variable's target state. So triggered, it might be a transition, might have or will have a target state that it's going to go to, okay? And then what I do is I start putting together a series of actions that I'm going to return out of the update function. So the update function is going to return a series of actions or an array of actions. I'm going to start off with the current state, whatever I am. I may have some exit actions, whatever those exit actions are. One or more actions that I'm going to take. Example would be if I'm in a melee combat and I'm running away, if that's a transition, maybe the transition action is drop your sword, run away, or put your sword away and run away, or put your shield up and run away. Who knows what you're going to do, right? But putting your shield up might be an action that you're going to take that is connected to your exit action, something that you're going to do, right? The other action you want to add in is whatever the triggered actions are. That's another action you're going to take. So you're going to put that into the action array, right? And then finally, is there any entry actions that are going to happen to the new state? Maybe when I go into the new state, and if I'm going to run away, maybe my entry action would be perform the run animation. I'm running, right? Or perform maybe there's a blend, an animation blend that goes from putting my shield up, as an example, to there might be an animation that I have to make, or some kind of other entry action that I might have when I'm moving from an attack state to a flee state, whatever that is. If there may not be any, okay, it doesn't mean that there are any, but what this does, this system allows you to have one or more actions associated with the transition, okay? And then what we do is now we're switching the current state to the new target state. So whatever that new target state is, okay? Otherwise, if nothing is triggered, just return and get the actions for the current state. Whatever I'm doing right now, keep doing it. That's what the current state, that's what the state machine class would look like, okay? A lot of times though, when we simplify things, we'll talk about this as an example. We'll talk about hard-coded state machines and how sometimes we do that instead of doing something like this. This is a class, so what we can do is we can set up a state machine, a different kinds of state machine for each enemy, as an example that is in play. Let's talk about some additional data structures and interfaces. So the state class, right? So each state is going to have, and we can also use a struct for this, but it might have, as an example, a number of different actions that it currently takes, an entry action, an exit action, and a set of transitions. All right, so that's what each state will have. Okay, so one or more transitions, entry actions, exit actions, and so on, right? And whatever this get actions method should return a list of actions to carry out. So it could be, notice that there is an array of actions and an array of transitions from each state. All right, that's very interesting. And then the transition class, then if we look at the transition class, is going to have several different functions as well. An is triggered function, right? So which returns a Boolean. Usually the is triggered function is going to use some kind of condition or test a condition to make sure that it's triggered or not, okay? And the other one is get target state. What is the new state that it's going to go to, right? I'm going to transition to the next state. What is the next state that I'm going to? The one that's connected. This transition connects from one state to the other state. What's the next state that this transition connects you to? And finally, what are the actions that this transition has associated with it, as an example? Okay, so that's very interesting as well. So again, it looks complex, but again, what we're trying to do here is make a generic state machine that fits for multiple situations. Okay, not a single situation. Okay, that's the idea behind it. So we talked about transitions and everything else. A lot of times state machines are defined in a data file, and what we do from the data file is we read in we kind of construct, and by the way, decision trees and behavior trees, also a lot of times we have a data file that we read, And it's easier for the programmer to put together a data file. And the data file is going to have a series of actions, states, decisions, conditions, a bunch of stuff that kind of is put in there. So again, that it's not necessarily hard-coded, but we construct the state machine typically from some kind of file, typically. Now, it doesn't have to always be that way. Maybe we just, we have a way of adding a state and adding a transition and adding an action and all those kind of things, as an example, compared to other helper functions that can help us do it in real time, like through, build state machine for whatever kind of enemy you're making, right? So kind of some kind of build state machine method. But a lot of times it's just easier to use a data file, right? And it's common. We want to be able to read from that, as opposed to us, putting it together. Okay, so that's what that is. So unlike decision trees, state machines don't provide some kind of easy way of combining tests to make more complex tests. The conditions let's talk about the condition interface and see what that looks like. So here's transitions, like we talked about before. Here's the transition class, right? And the transition class might take more. Here's some more detail. Basically the same functions that we had before, with some additional parameters, right? So we have an actions variable, an actions array, which is a series of actions. We have a target state, as an example, and we have a condition, right? And the condition is the thing that's going to trigger, as an example, change the is triggered function to either true or false. Usually what it does is it takes that condition, we test that condition, and if the condition passes the test, so it's true, then we trigger the transition. And when the transition is triggered, we move to the target state, whatever that is. Okay. So what then does the condition class give us? Typically what we have is, and let's think about this as a superclass for conditions, right? It has a single function typically, that is the test function, right? And the test function allows us to return either true or false, right? And we can make more complex conditions. For example, we can have a floating type of condition, very similar to what we did with decision trees, where we have a test value, and that test value, if it falls between a minimum value and a maximum value, then the condition is true. Otherwise, it's false. So that's the float condition example. And what it does is it extends the condition superclass. Okay, condition superclass would be just a Boolean. All right, so that's the way it would work. So very similar things. So we have a condition, we have a transition, we have a state. Okay. And we can have other ones too, the and condition, the not condition, and the or condition, where we kind of can take two conditions, condition A, condition B, and if both condition A and condition B must be true in order for this condition here to be true, and so on. So you can say, I need both line of sight and I need to be within attack range, a melee range, in order for me to trigger this one, which means this and condition might be something like, the can I attack, kind of thing. And the only way I can attack is if I have these two conditions met. Okay. And the not condition means like, okay, I do not have low health, right? So if I have low health, right, then then I would run away. But if I don't have low health, then I keep fighting. That would be the not condition, right? And the or condition is either one or the other. So for example, if I have line of sight, or I have the players in sensing radius, as an example, if one of those conditions are true, then I know the players on this, we've detected the player. If the player's been detected, now we're going to take a series of different kinds of actions based on that information. That is the internal state now that we have. Okay, so different kinds of conditions that can be triggered. So let's talk about, we talked about really interesting things and how finite state machines would work, but we also should talk about some weaknesses. So one of the things that is we have a lot of method calls happening. One, we're going to have our stack is going to be full of different calls, from one state to the other state, from one state to the transition, from the transition to its set of actions. There's going to be a lot of function calls. And so because the method calls have to be polymorphic, right? So that means they can be modified as we go forward. It's going to slow down the call processor, and the call processor is basically the call stack. There's going to be a lot of stuff on the call stack in this case. Now again, for most modern hardware, it's going to be is it slower than a decision tree? Yes, slightly, as an example, but for the most part, we're not going to see it. We're not going to feel it. If I was doing this, however, for thousands of AI units, let's say across a massive battlefield, that would be a different case altogether. Maybe this wouldn't be the best way of doing things in that particular case. We might want to use decision trees. If the decision is really simple, a true false kind of condition, decision trees are the way to go because they're much quicker than finite state machines. Sometimes what we also do is, especially when you're a beginner, you start off with thinking about a hard-coded state machine instead of making a state machine that is a class-based, object-oriented state machine, the way we just talked about right now. That was the harder way of doing things in many ways. So how does this look like? We might have, like we said before, some kind of enumeration like a patrol or defend or a sleep. And then what we would do is we just hard-code it. So we'd say something like, if my state is equal to patrol, whatever my state is, if I can see the player, right, as an example, then my state changes to defend, okay? And then we exit this part, and it comes back into the update state. And then if my state is equal to defend, then if I can't see the player, then my state is equal to patrol. So I can move out of patrol again, go back into the update function, and go back into patrol if I can't see the player, right? And if I'm tired, right? So I can't see the player, and I'm tired, then my state is going to be to sleep, right? As an example, and maybe I'll go to sleep for a particular time until I'm not tired anymore. And if I'm not tired, then I'm going to switch back to patrol. Okay, so very, very simple way of doing things. And there's also other little functions like notify noise if noise is heard, right? If my state is equal to sleep and the volume of noise that I'm getting is greater than 10, so I heard the player, then I get up and I'm in defend state right away. I'm not even in patrol state because I've heard the player. I'm back into this state. So this idea is a way of making a hard-coded state machine. So what is a problem? What would you think, guys, is a problem with doing this? Because this is something that we could do, and it's much easier than doing the finite state machine we talked about earlier. So what would you say is a problem with this thing? What would you say? And again, I know I've talked about a few things. Let's recap, okay, a little bit. We've talked about states. So states are almost like a situation that your autonomous character's in, as an example. I'm in a specific situation. I'm taking a particular action. All right. Remember, a state or states are linked to actions, whatever those actions are. So I'm in a specific state. Okay, cool. I have a bunch of transitions. I can go from one state to the other state. What are the types of transitions that you can see here? Right. There are no transitions explicitly listed, but we do have transitions. I can go from the patrol state to either the defend state or the sleep state. So those are the transitions that we have. And if we were going to draw this finite state machine out as an example, right? So we have patrol, right? And it can go either to defend, right? Or I can go to sleep. That's what I can do. So here's defend, right? And then there's sleep. Okay, those are the two states that it goes through from patrol. Because patrol is my default state. That's where we start off. Okay. And what about defend? Defend, again, the only thing I can do is go back to patrol. Okay, so that's what I can do. Defend can only go back to patrol, and sleep can only go back to patrol, right? So if I'm not tired, right, that's the case. But the only thing I can do is go back to patrol. Okay, notice that there is no, going from, there's nothing that says anything about going from defend to sleep or from sleep to defend, except for this part right here, which can be quite confusing. This could actually be something that's put into the defense, the sleep state, right? Sleep, which is this one, should be able to go to defend if, as an example, we've heard a noise. That's what happens. Okay, that's what can shift us from here, from sleep. This is sleep, and this is defend, right? And this is patrol. Sorry for my crude drawings, but you understand what this works. So this is what we're doing here. And what we're doing is we're hard coding it. So what would you say is a problem with doing something like this? Anybody? What's a problem with doing this? Come on, guys, I have a lot of intelligent people here that we can use. Okay, Simon says you have to list every specific possible action. Yes, that is definitely an issue, right? Here's something else. Simon, what if I wanted to change this thing? Or what if I wanted to set up a finite state machine for 3 different types of enemies, right? What would I have to do then? I'm going to have a lot of duplication, right? This is going to be duplicated a bunch of times over and over again. I might have a patrol state, and some enemies might have, instead of defend and sleep, they might have, defend and raise the alarm. That might be something that goes from the patrol state. If I can see the player before I get into defend, maybe I can raise the alarm. Maybe I can attack. Maybe I can do whatever I want to do, right? So this is an issue. This is an issue where I can, I have to duplicate a lot of my code. And code duplication in general is a bad thing. Okay, so that's why hard-coded state machines aren't preferred. Can we do them to test? Do I do them? Remember, my motto is make it work, then refactor. And as long as it works, at least we have some kind of thing that's operating for our game. All right, so again, we talked about how each of the transitions work. The update function is called each frame, okay? And as before, and the current state is used to generate an output action. And to do this, the finite state machine might have a method containing conditional blocks of the following form. So here's an example that we talked about already. So so let's talk about weaknesses. Although hard-coded state machines are easy to write, we can think about them really easy. They're difficult to maintain, which is exactly what we talked about. State machines in games can get really large, and this can appear as a crazy, ugly code and really unclear as what's happening. You have to literally go and try and trace, if this is much larger than this, what's happening. So again, if I'm going to write AI behaviors for multiple characters, multiple autonomous characters, then again, I'm going to copy and paste a lot, and that is also a big issue, right? So it's not maybe a problem for a small game if I only have one type of enemy, or a scene where I only have one type of enemy. But if I have multiple enemies, or if I wanted to make it more robust or expand my game or something like that, we're going to see a lot of duplicated code that is very difficult to maintain and coordinate. Okay, so it makes it less flexible, is the idea, compared to how we've done it before. All right, so that's kind of like, before we go on to the next piece, which is a bit more challenging to understand, right? Does everyone understand the basic idea of state machines? If you understand, check mark, please. If you don't understand, you're not getting it, X for those people that are watching the video. Let's see how you guys are doing. Lucas is good. David is good. We've got Shelly and Simon and Stanislav. How about the rest of you guys? Are you getting it? Not getting it? Any questions? Before we move on to something more complex. There's no half check mark, Christian. No, either you get it or you don't. All right. So Jack says he understands. Okay, good. Thank you guys for that feedback. I'm going to move on. So one thing to note, guys, is, again, if you don't understand regular state machines, then hierarchical state machines, well, that's going to be more difficult to understand. So really, state machines are really powerful, but sometimes it's difficult to express some types of behaviors. And again, one common source of difficulty is the idea of alarm behaviors that we just talked about. So the player raises an alarm. Okay, that's a new state. But it's not just a state for, maybe it could be an alarm state could be something that's for multiple enemies, as an example. So we could have a state machine to do this. And here's an example of, a regular a normal state machine. Okay, so a normal state machine, again, if we had a little robot as an example, let's suppose I had a little robot, that's the condition. And the little robot is, so imagine I have a service robot that moves around a facility, cleaning the floors. It has a state machine allowing to do this, right? It might search around for objects that have been dropped, pick one up when it finds it, and carry it off to the trash compactor. And this can be implemented using a normal state machine like this. Okay, so again, I enter in, I have a search state. So this is not an enemy, but rather a robot that's wandering around the station, right, as an example. And I have only one transition. I saw trash, right? That's the condition that transitions from the search state to the head for trash state. I want to get closer to the trash. So I get closer to the trash when I'm close enough. If I am close enough, I can get the item. When I get the item, I go back to the compactor. When I go back to the compactor, I dispose of the item. And then once it's disposed of, I can go back to the search state. So very simple way of doing things. Okay. But what happens if the robot runs low on power, right? Which is an alarm state. We talked about alarm states are the things that can kick a regular state machine out of normal operation, right? So what happens then? So regardless of what it's doing at the time, right, no matter what state it's in, right, we should be able to transition it from, you know, its current state to the low, I'm in low power, I need to recharge, right, no matter what I'm doing, okay? So, and again, recharging periods could allow the player to sneak by unnoticed, for example, or allow the player to disable all electricity in the area and thereby disable the robot, okay? So leaving the current action to become recharged is an example of an alarm mechanism like we talked about before, right? So representing this in state machine leads to a doubling in the number of states, right? Because think about this, if I had an alarm, right? So if I had an alarm condition that I drew right here, let's try it. So let's think about this as an alarm condition, and we'll just draw another box over here, okay? So if this is the alarm condition, so this is like low power, right? The low power, which is an alarm condition, can I have low power from, let's put it here as an example. I can have low power from any other, you know, kind of position, right? I can have low power from my compactor. I'm heading to the compactor. Before I go to search state, I run out of power, so I can go to low power. Can I go from heading for trash to low power? Yeah, I'm in a low power. And I can also go from searching to being in low power. So I can have all those three things. And now I'm literally doubling the number of transitions, right? Because I have 1, 2, 3, and now I have 6 just by doing this, right? And what about if I go from low power? I'm not low power anymore. I go back to the previous state, so I can go back to there. And then from low power, I can go back to head to trash. From low power, I can go head to the compactor, right? So just having this one state adds a bunch of transitions, which makes no sense, right? Really, if you think about it, low power is an external state that has nothing to do with its actions, okay? So this is where we can get a little bit more interesting in the planning of our, you know, kind of our thing, right? So really, when we think about this, we have this situation here where I added, you know, get power to a lot of different things. I just kind of drew this state machine a little different than this one. But at the end of the day, we don't want this state machine to be in place because it doesn't make any sense. In essence, what we want to do is when we create a hierarchy, we have an upper state, and then we have a state that is a substate, if you will. All right. So each of the higher states or lower states, if you think about this, are the things that we want to transition to. And there should be a transition from a higher level state to a lower level state. Okay, we'll talk about that. And that's kind of what the idea is. I'm not going to read through this, but for the most part, what I'm talking about is things that we've talked about already, right? So here's an example. Get power would be an external state, okay? Get power would either have, there's only really 2 states in this higher level state, either get power or clean up. So you can see that the cleanup state has several substates, okay? And the substates that we've talked about already, all right? So really what happens is, notice that the little black dot points to cleanup right, as the initial state. We're not in get power. We're already powered, let's say, right? So we're in the cleanup state. Okay, so now what do? I have a state machine within a state machine, and I start here. This is where I start off. I start off searching. And when I'm done, right, as an example, if I run out of power, it's going to trigger my no power state change to go from cleanup, right, to the get power state. So I'm leaving these states to go to get power. And then from there, I'm going to go back to cleanup, and cleanup, I'm going to go back to search, right? Or, whatever the last thing I did was, okay, as an example, which is kind of interesting, where you can keep track of which internal state or substate was I in last, and go and finish that thing off, whatever I didn't finish. That'd be the smart thing to do. So a hierarchical state machine is refactored, if you will, right? It kind of groups states that are make sense together, right, into another state. Example, cleaning up or getting power. Getting power could also be something that looks like this. Where when I get power, if you want to be really more realistic, I have to move to the power. I have to get into the station. When I'm in the station, I have to wait for for my power to be up. And when my power is done, then I can leave the station, collect my trash. Like there's going to be a lot of little mini states in here, or substates inside of the get power state that allows me to go back. So check to see if I have to put the trash down before I power. Maybe I can't hold the trash, as an example. Or maybe I have to flush the trash first somewhere in a temporary container and then move back to cleaning up again, right? Lots of different things that I can do. So again, most hierarchical state machines support transitions between different levels of hierarchy. That's what we want them to do, because if we don't support those transitions, then how would we perform the substates? Okay. So again, you could kind of set up this thing where we say we keep searching. If no trash is found, we looked around the station for a while. We can keep looking around the station until your power runs out. But if we've already done a round of the station, just go back and get power for a while, right? And when your powers up, if you've looked around once in the station and you haven't seen anything, then go look around again. And if you go look around again, and if you don't find anything, go back and power up again. So you don't even head for any of these two things if you don't keep searching forever. You can kick yourself out of searching and into getting power, which is kind of a neat way of doing things. All right, so again, here's the problem with hierarchical state machines. We want to implement a state machine system that supports hierarchical state machines. We'd also like transitions that pass between different layers of the machine, so that way we're able to have more complex behavior, which is what we're looking for, right? And when we look at the algorithm, again, a lot of times we use recursion to do that. Recursion means we call a function from itself, right? A lot of times when we use recursive functions, we need some kind of termination state, like we've talked about before. Very similar to what we talked about last week when we said decision trees are often also recursive. And the reason why they're recursive is because when you might be in a loop where you're calling the same kind of decision over and over again, similar to a search algorithm. Search algorithm can be very recursive. So really what we want is, when we talk about the algorithm, the first part of the whole system returns the current state, and the result is a list of states from the highest to lowest in the hierarchy. So that's what we want, okay? And the state machine asks its current state to return to its hierarchy, which is interesting. And if the state is in a terminal state, it returns itself. Otherwise, it returns itself and adds to the hierarchy from its own current state. And this is where the recursiveness of the algorithm can be quite complex. Again, here's what it might look like. So we have a state L and a state M. You have, and this is just example, who cares what these internal states are, but we have an initial state, which is state L. In state L, we have a series of substates that we want to keep track of. And we're going to start off, because L has its initial state internally, it's going to start as state A. That's what that means. So the second part of the hierarchical state machine is its update function. And in the original state machine, each state machine started off in its initial state. But because the state machine always transitioned from one state to another, there was never any need to check if there was no state. So what if there is no state, like a null state, if you will? State machines in a hierarchy can be in no state, and they may have a cross-hierarchy transition. This cross-hierarchy transition, which is a very special type of transition, is the way we're going to go from one level of hierarchy to the next. Okay? So again, we want to be able to do this cross-hierarchy transition. Maybe there's some kind of states from within a substate to an upper state, in the hierarchy, as an example. And we might have a transition to go from one internal state to an external state. Okay, so again, let's take a look at something that might be some pseudocode that we might use for a hierarchical state machine, as an example. And it might look something like this, where I have a class where I have the update result, right? And the update result, notice that there is a class inside of a class. A lot of times we might use a separate class as well, but notice that it has different kinds of, the inner class might have a number of different functions, actions, transition, and a level, right? Whatever that is. And then what we want to do is the get actions method of the hierarchical state machine base class, as an example, might have a return, get actions returns an array of actions, out of it. What actions are we going to take? And then this is where it becomes more complex. The update method of the hierarchical state machine returns some kind of update result, either an action, a transition, or with the level that we're in. One of those three things. So example would be the update result. We make a new update result, temporary object result, and we say that result.actions is equal to get actions, whatever the actions are, that we're currently taking, as an example. The result transition starts off as null, so we don't have a transition. The result level is 0, so that's the highest level, the 0th level, or the base level, if you will. And then we return the result back out. So that's what this does with the hierarchical state machine base, right? We also have another function that is get states, and what get states does is it returns an array of states, okay? Again, we don't implement this in the base class because our base class is meant to be inherited. This might be more of a abstract class, and then a concrete class would inherit from this class to create a series of states. Okay, so again, very, very high level pseudocode. The transition class, when it comes down to it, would define a couple things. I would have, get level is triggered, get target state, and get action, right? As for before, these are all things that the transition would have. All right, so that's the transition class, and your submachine state, right? So your subclass, right, would basically inherit from the hierarchical state machine. Okay, that's what it would be, right? So it's going to extend the hierarchical state, and it's going to implement the state interface. That's what it's going to do, right? So you might have, a get action, which returns a state, right? An update, which returns a hierarchical state machine update. It's going to go whatever the hierarchical state machine it's inheriting from. It kind of calls the update function of the superclass, right? And get states, as an example, if I'm in my current state, then return a number of the current state substates. So each current state would have a bunch of substates, if any, else return this state itself. So if there's no substates and there's only one state that we're talking about, then just return this. And this is, again, a little bit more complex to think about than we've seen in the past. So here's a state machine without decision tree transitions, right? By the way, one thing that we want to do is we want to combine, these are out of order. Sometimes we can combine state machines and transition and trees together in one. And the great way about this is, here is I have an alert, right? Here's a tree structure, and I'm in the alert state, right? Can I see the player? That is, a condition. If I can see the player, right, then is the player nearby? Again, we're in the tree right now at this point. If the player is nearby, then switch to defend state, okay? and whatever those substates are. So this is a hierarchical state machine where I have 3 different state machines: alert, the alert state machine, the defend state machine, and the raise the alarm state machine, which has a bunch of separate substates. And we can use a decision tree to get us there. So combining decision trees and state machines. Kind of neat, right? What would it look like if a state machine without a decision tree? Well, then you say, here's my alert. And then if my player is in sight and the player is far away, then I want to raise the alarm. Otherwise, if the player is in sight and the player is close by, then defend. And again, this is a hierarchical state. So alert, raise alarm, and defend would have several substates inside of them, potentially. All right, so that is state machines at a very high level. Again, I think they're a great tool for us to use when it comes to making decisions, okay? And they're a good tool because they're easy to understand. State machines are easy to understand. And, they're a different way of making decisions than, let's say, using a tree structure. A tree structure, you have to put together a different kind of you have to code it in a slightly different way. You have to create a different data structure. Where here, a lot of the guts of the data structure are there for us. A switch case, a lot of times, what we might use, to kind of move us from one state to the other state. That's typically what we would use, okay? Or at least we use a switch state for the conditions. We would check conditions. Depending on the condition, we would switch from one state to the other state, okay? But with a decision tree, it's a little bit more challenging in terms of setup. It's fairly simple, but really it basically gives us, just like we saw here, a yes or no kind of situation. Either it's true or it's false. Whereas state machine can have a bunch of different actions. States are linked to actions, as an example. Whereas in order for me to get to the action in a decision tree, I got to make several decisions before I make that final action. Okay? So that's something or I have to answer a bunch of questions. Can I see the player? Yes. Is the player nearby? Yes or no. And if my player is nearby, then I finally take an action, as an example, or I go through a set of actions in the decision tree. Whereas in a state machine, I literally just move from one state to the other state. Different way of doing things, but the results might be the same. All right, questions around state machines. What are your thoughts, guys? Would you use them? Would you prefer them over trees? What are your thoughts? Hopefully you have some thoughts around this. You're all programmers. You're all thinking about AI potentially. What would you do? Would you use more for up to now, things we've talked about last week and this week? Would you use a decision tree if you're plotting out your your AI brain, a state machine, or a combination of both? What would you do? Anybody? Christian says it would do straight states. Ethan says state machine. Okay, so question, why states and not decision tree? Why not? We talked about the weaknesses of a decision tree. We talked about the weaknesses of a state machine. Why would I rather use a state machine a lot of times rather than a decision tree? What are your thoughts around that one? Because only a couple people answered. Christian says, I don't remember how trees work. Okay, fair enough. Raul says less complex. Yeah, they can be less complex. To make a generic state machine, not a hard-coded state machine, can be quite challenging, right? Because think about that the setup that we had before. If I go back to that earlier structure that we thought about when it came to the pseudocode, right? So when we're not hard coding, think about this. The data structure itself for the state machine. The state machine itself has its own update function. And the update function itself is the thing that's going to be going through and check to see if a transition has been triggered. All right, so that's a very different way of doing things in than what we're used to by using a switch case. Christian says state seems more versatile. Well, they create a different combination of conditions, not necessarily more versatile. Remember, I can always convert from a state machine, right? Or from one thing to the other thing, if you think about it, right? So let's do that example. Okay, so let's suppose I want to transition from, we're just going to go to a very simple state, not a hard-coded state. Let's go back up to what we saw earlier. All right, so we have this. This looks like a bunch. I have a bunch of different states, right? And this might be something that is coded in a state machine. All right, so I start off. Let's say my initial state is wander or patrol. Okay, as an example, and from there I have one possible transition out, as an example, and it's if the player is near. Okay, so could I make this into a tree? Right? Or could I make a tree into a state machine? Can I go both ways? How about that? Let's think about this for a second. So if I was going to draw the tree out, Lucas says prefers the tree for simplicity, but state machines are best for numerous situations and linking each to one another. Yeah, I mean, I think, to me, I like the tree structure a lot too. I think that combining both tools, remember, these are just tools that we can combine from one thing to the other. But let's suppose I have a tree structure to represent this thing. So at the top of the tree structure, as an example, we start off with a particular action that we're doing. We're in wander or patrol state. And then I want to have some kind of true or false. So if I was going to kind of start off with this situation, I might say that, well, do I see the player if the player is near? So that might be a thing that comes from the tree. Okay, cool. If the player is near, then I'm going to go into attack, right? That's what I want to do. Okay, so let's plot that in and this is like a leaf node because we're getting into the action right away. If I start plotting it out, and let's see how this looks as an example. So I have the next piece is I have another action which is attack, right? Okay, from the attack action, the only place I can go back is players out of sight. I'm going to transition back. Do we ever have a way of transitioning back in a tree structure? I'm going to move from attack to wander. Well, it means that we have a way of going kind of back out with the tree. So I can kind of do something that looks like this, right? I can go this way, right? But I also can do from attack, as an example, I can also think about going to evade, right? So I can go, okay, well, if from attack state, if the player is attacking back, then I evade, otherwise keep attacking. So is the player attacking back, right? Otherwise keep attacking. So keep attacking means stay where I am, right? So that's what it works like. Let's see if we can do this. Okay. So this doesn't really look like something like a tree because trees don't go back, right? They don't go back to a previous state typically, right? What happens is, right? So, and we don't record this line, but let's take a look. So, all right, so we can go to evade. So here's evade. Can I go to something else from evade? Yes, but notice it's like almost like a linear track when I'm in this particular case, right? So let me try this out again. So again, I'm in evade. The only place I can go from evade is, I can go back to, if I'm in evade, I can go back to attack, right? If the player is idle, or if I'm in evade, I want to go to find first aid. All right, so we're going to find first aid because there's only one condition, right? So we'll find first aid, and then we're going to put that over here, right? So take a look at this. It's like a deep tree, right? It's like I got one action, and from the other action, I go to this action, and really that's what it looks like, right? It's kind of looks like this, right? If I just follow this idea, right? And really, this isn't the way to do it. This isn't the way to do it. Where I would start off, if I was going to convert from one thing to the other thing, right? If I was going to convert, I would look at this. Health points are low. Okay. Player is attacking back. Player is idle. Player is near. Player is out of sight. Found aid. Okay. So again, if I was going to do this, right, and restructure this as a tree, let's put this aside for a second. How would this tree structure work? I would look at the conditions first, and these are all the actions. That's what I would do. So I would kind of convert it back to leaf nodes. So the first condition is I'm in wander. That's my default state, right? As an example, is the player in sight? do I have line of sight with the player? If I don't, what do I do? Then I go back to an action, which is the wander state, or let's call this the patrol state. Okay, so let's do that first. Do I have line of sight? So that's my first condition, and that's the thing that I would put in there. Okay, so line of sight would be the condition. Let's say line of sight, and then once I have line of sight, it can determine what I want to do. I can attack, right? As an example. Now maybe when I'm in attack state, the other thing is, what about my health points? What about if my hit points are low, right? My player's in line of sight, but my health points are low, right? What do I want to do? So that is something that, can I say that I can link my different things together, right? So example, the next condition would be something that looks like this, right? So let's continue for this. So the other thing would be something like, is the player near? Let's draw a line, Tom. How about that? So let's go, is player near, right? That might be the next thing. So here it is. We'll just put the word near, right? If the player is near, then what do you want to do, right? Then you want to attack, right? That might be a state that I might get to. Right, so if I'm near, then I do an attack. I do the attack action right here. Okay, so that's the action I'm going to take. This is the leaf node, right? Okay, what about going back to near? If I'm not near, right, then what am I going to do? Then, well, this doesn't make any sense, because if the player is not near, right, then I have line of sight. Maybe I want to move near, right? So if I'm not near, maybe I want to move. That might be an action that I want to take. I don't have that inside here, but it's implied, right, that I'm going to somehow move to the player. So maybe this would be move, right? Move near. I mean, I need to move to attack, right? What am I going to do, right? Okay, just follow me here for a second, guys. So I'll move near. That's an action. This is an action, right? Okay, now what if I don't have line of sight? Well, if I don't have line of sight, then, I'm going to patrol, right? Because I don't have line of sight. I've never detected the player, as an example. So if I haven't detected the player, right? And if I don't have line of sight, what's my health like, right? Maybe that is the next thing I want to check. Are my health points low? So that's something I can check. So if I don't have line of sight, so this is yes, right? So let's put a yes in there. So if I have line of sight, if I am near, right, that's the yes track. This is all the no's, right? If I'm going to set this up, this is no, I don't have line of sight now, right? As an example, if I don't have line of sight and, do I have health points? My health low, health low? Is my health good? As an example, I'll put this health. Is my health good? If my health is good, then what do I want to do? I want to patrol, right? So what do I want to do if my health is low? If my health is good, I want to do the patrol action, right? So let's put that down here because I can't fit it in. Oops. So maybe I want to patrol. If I don't have good health, then what do I want to do? I want to find aid, right? So if I don't have good health, I want to find aid, right? And let's just kill this and move this over a little bit so we can give ourselves some more chance to think about this, right? So I don't have health, then find aid. Now it's slightly different than what we talked about because this is kind of pathological anyway, the way this is drawn, right? So find aid. What about this other condition that is the health points are low, right? A lot of times we can see this health points are low as an alarm condition, right? Because if my health is my health is good for some reason, or whatever, then I can patrol. Maybe instead of health being good, it would be am I tired? No, patrol. If I've got energy, patrol. If I don't have energy, sleep. That could be something that I do. But for many of these states, this is, if you think about this tree structure, there might be an alarm condition that kicks me out of this, because I can create another hierarchy when I don't just do this tree. I just kick myself out into some other kind of tree altogether, right? And if I'm in an alarm state, right? For example, if my my player is attacking me, right? Then that might be something else. Do I have line of sight, right? Near, yes. Is my player near? Yes. Is my player attacking? Is the player attacking? Yes. Evade. If the player is not attacking, attack them. If they're not attacking me, right? And then, I'm near, and is my health low? Then maybe evade, right? Get out of there, right? Find aid, which might be another tree that I could create. The idea is that we can try and convert from one to the other, and they're very interesting. What about converting from a tree structure back to a state machine? How does that work, right? So trees to state machine or state machine to trees, it depends on, you can see that there's difficulties going from one to the other, but we can represent the same actions mostly with both. Okay, just letting you know. So again, lots of great ways of thinking about this. We would structure it differently, and the effect would be slightly different than this, right? Because a state could have multiple transitions that it can make, typically, right? So more complex in many ways, right? Whereas a tree, it's very simple. It can go left or right, yes or no, true or false, typically. Typically, that's what we do. The reason why it's really fast is because we can get to the correct decision and then go back and loop around again and go, okay, so where am I doing? I'm in the attack action. Okay, now that I'm in the attack action, am I still attacking? Am I still in that state? Because that's a state, right? Combining them is really powerful, because what you can do is you can use the tree structure to get you into something like the attack state, right? And then in the attack state, as a hierarchical state machine, you could have many little things in there. For example, I'm in melee attack. Okay, cool. Do I have an alarm state that kicks me out of attack state? Yeah, health points are low. That's the alarm state. The alarm state is going to move us out of that lower level state machine into something like, I got to flee. I got to do something else. Okay, so, and that might be something else that we might set up later on. Let's take a look if we can make, a state machine as an example. Can we think about a state machine that is working around your assignment that we talked about before? I just want to kind of explore this before we go for the day, and then we'll get back to this. Okay, as an example. And let's see if we can draw them out, something like this. And we'll use state machines as opposed to trees today. But again, the idea with the assignment is that we understand how it works. Let's take a look at assignment 4. Again, assignment 4 has been released from before, right? And this is the big one. This is the one that we want you to work on. Again, due by April 17th at midnight, 3 members, right? We have a set of actions: patrol, move to player, close combat attack, flee, move to line of sight, move to range, move behind cover, wait behind cover, ranged attack. Those are all the different kinds of actions that we can take. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different actions. Okay, which is kind of a little bit imbalanced in terms of the way it works. There's also some sub actions. Close combat attack animation might be something that's linked to the close combat attack state, okay, if you will, right? And there might be other kinds of actions that you can make related to that particular state. For example, move to line of sight, you'd play the move action, the move animation. Play the move animation might be another action that you're going to take, a series of actions that you're going to take inside of the move to line of sight state, right? Or when we're transitioning from one state to the other state, I'm playing the move to line of sight action. That's part of my action array that I'm making, right? Move to range, I'm also going to play the move to animation, play the move animation inside the move to range, right? So another action I'm going to play. Move behind cover, right? As an example, I'm going to play the move animation, right? I'm also going to find the closest node to the player. Funny enough, we're going to make you find the closest node to the player this week, right? As part of your lab. That's part of the output for your lab this week, right? So wait behind cover, that is an action that we're going to take. So let's take a look at the close combat enemy loadout. So starts in patrol action. Okay, so let's map this out. So we'll map it out as a state machine, right? So we'll see how we can do this, right? So let's start off with our little box. So this is the patrol action. So we're in patrol. If I can actually type. There we go, patrol. And in patrol mode, what does it do? Okay, so it continues this action until they have detected the player either by line of sight or the player is within their detection radius. Okay, so if the player has, it's an either or condition, right? So that means, so the condition that we're talking about, that we're testing for, the condition is either line of sight or radius. We'll call it detection radius. Okay, so that's the condition to kick us out. If we have line of sight or we have radius, those are the two conditions that that can move us out of this thing, right? So those are the conditions that are gonna kick off the transitions. Okay, but what transitions can we make? If I have if the player is in their detection radius and they do not have line of sight, so I only have detection radius but no line of sight. That is a condition. So one is yes, the other one is no. So that's kind of the transition. So radius and let's put this in, and not line of sight. If we have that, that kicks us out into a another thing. And the other one would be, what's the other transition? So so if the player is radius and do not have line of sight, if they have line of sight, then they do something else. If they have line of sight, so that's something as another transition, line of sight. Okay, we'll move that over here. Okay, line of sight, radius. Okay, and if they have line of sight and is within close combat distance, so line of sight only, but far away. So this is what that would be. So line of sight, but not close. So line of sight and not in close combat range, not close combat, we'll say close combat range, right? That is one. That's a condition. Okay. And what's the other one? You might have line of sight and close combat distance, right? So let's take a look at this. Line of sight and close combat distance. So that's the other one. If I have both, those are different conditions. Okay. Let's take a look at that patrol state. Okay, the central state as an example. And again, I'm just drawing the linkages between them. And the other one is if the character's health drops below 0. Okay, this is an alarm state. So this is an alarm state. So we're not going to put that here. This is something that we're going to put over here. So this is if this is outside. So health low, right? Health low. We're going to do a flee, which is going to get us out of this whole thing altogether. Okay, we're just going to put that over there. So why have I drawn this? Because this is the close combat enemy, right? So this is the close combat enemy, CCE. They start in patrol state, right? As an example, when they're in patrol state, if I have radius and not line of sight, so again, if I go to, if the player is in detection radius and does not have line of sight, I want to move to line of sight action. Okay, so let's make that as another box. Move to line of sight action. Error. So we'll put that over here. So move to line of sight. So I'm moving to that's my state, moving to line of sight. Okay, and I'm going to come back to this. Move to line of sight action, and that is a something that I'm going to do from my patrol state. So my patrol state moves me to line of sight. Let's see if we can draw this out. And what about if the other case where I have they're in my radius but I don't have line of sight? Well, if they're in my radius and I don't have line of sight, then I want to move to line of sight. So that's the other thing. So this is the, if the player is in the detection radius and they do not have line of sight, that was actually the wrong one, but we'll move that over, no problem. That's the great thing about this little tool. You can move this over here. This is what it should be. All right, so this is the transition. And I'm drawing this out for you because I want to try and help as much as possible. I don't want to hinder. That's not the intent here, right? But I want to move to line of sight, so I got to do this. What about line of sight? And I have line of sight, but I have line of sight, but I'm not in close combat range. I have to move to player action. So that's what I want to do. So let's do that over there. Move to player. Move to player. That is the action that I'm going to take, or that is my transition. That is my state. I'm moving to the player. Okay. And all right, cool. If the close combat has line of sight and is within close combat distance, do an attack. Close combat attack. I guess that's this one. Okay, I'm just going to draw them out. Close combat attack. So CC, we'll call it CC attack. Okay, that's this one. You draw it this way. Okay, what about, let's talk about these other conditions here. What about when I'm moving to the player? If I'm close to the player, right, then what do I want to do? I want to perform a close combat action because it says if I have line of sight and is within close combat distance, then do a close combat attack. So this would be from here to there. I'd have a transition that goes from move to player to close combat attack, right? So move to player. So when I'm close combat range, right? Then that's true. I already have line of sight because we're moving to the player because I had line of sight. So I'm maintaining. I'm recommending that I maintain line of sight and I move here, right? So I move transition from here to here. Okay, cool. What about if radius and I don't have line of sight? I move to line of sight. So moving to line of sight. Okay, cool. I see the player. Now I got to move to the player, right? So that goes from this. Let's see if we can draw this together. From this to this, right? That's kind of, can I draw with this tool or what? I'm just trying to draw arrows. So again, if move to line of sight, if I have line of sight, but I'm not within range, then I move to the player, right? So that's the thing I have to do. So line of sight, then I move to the player. Once I have line of sight, move to the player, right? The other option is, what if I'm close enough to the player, right? That's also one thing. If I have line of sight and I'm close enough to the player, then attack. Because that can happen too. I'm in patrol, they're in my radius, I'm moving to line of sight. When I get close to line of sight, I'm also close enough to attack. That could be a possibility. So that I could also do something that looks like this, right? So I could do this, right? And again, we can draw this in different ways, right? But I'm just showing you this. This is one possible drawing, right? And this would be close combat range. These are the same conditions. Take a look. So it's close combat range. I'm in close combat attack, right? And what else? Close combat attack action. If the health drops below 25%, then I flee. There's nothing that says that I'm going to go back into patrol. Once I'm in close combat attack, the way we've planned this out is your enemy is going to keep attacking until their health is low. And if their health is low, they're going to flee, right? And the flee action is not part, if we're going to use a hierarchical state machine, the flee action is not something that you want to come from here. What if the player sees the enemy, right, and knocks this is nothing to do with them in attack, right? If any time when the close combat enemy's health drops below 25%, they're going to perform the flee action. So then we can use a hierarchical state machine to represent this state right here, right? So this is the state that we're going to use, right? And let's actually draw it with a thing. We'll move this over here. Okay, so let's say this is the state, and we'll say this is the will be in some kind of active state, right? So they're in action or in active service, right? So that's what the close combat enemy is like, active service, right? And there's something that's going to kick them out of inactive service, right? Which is what we want. And that's another state that's over here, right? So this is inactive service, the same level. Typically we want to draw it at the same level, inactive service, right? And there's a transition. Okay, there's a transition that I want to get to that goes from here to here, and it's anytime from any one of these things, I can transition from active service to inactive service, just like we've done before. We can move from one state to this state here, and we can do that, because of health low. Health low. Health is low. That's the transitions. That's the condition. Transition to an active service. We're going to also, if we want to plot it out the right way, if we're going to draw the diagram correctly, and that might be something else that we might want to do. So here is a diagram where we have this filled in box. Let's see if we can do that. There's my filled in dot, right? And what we want to do here is we want to transition, from here. The default is to go here first. We're not going to start inactive. We're going to start as by default as in active service, right? And then what we're going to also do is going to have another little dot here, right? So here's a little dot, and let's fill that in. And that little dot is going to point to our patrol state, as an example. I'm just going to put it over here. A patrol state is going to be the initial state. Okay, so that's the patrol state. You could have put it over here too. Okay, so I kind of drew this ugly diagram, but the idea is this is what the state machine might look like if you're going to use a state machine. Okay. First of all, do you agree? What are your thoughts around this, right? And of course, what is the action I'm going to take when I'm moving from health low, right? The action is I'm going to flee, right? That is the action I'm going to take, right? The only action I take is flee, right? That's the flee action. Right? So health low, I transition to an active service by fleeing, if I can, right? I want to attempt to flee, and that's what might it be. Have I left the screen? And if I have, right, return this thing out. If not, then give player points. That might be something that's inside of the inactive service state. Sorry, let's go back to the questions here. So Christian says, wouldn't that situation be taken care of automatically? It would just do nothing and move to player. Well, when we go to move to player, that is an action. I'm moving close to the player, right? But what if the player keeps moving away, right? Remember, this is the dynamic, right? So it's not like the player is going to stay in one place, right? So I move to the player wherever I thought the player was, and the player moves away. I move closer and closer to the player. I'm trying to attack the player. I can keep on seeking the player. That's what move to the player might be, right? And when I get close enough to the player, right, when I'm in close combat range, I attack, right? That's what I'm doing here with the player. What if I lose line of sight, though, right? That's also something that can happen. That's one transition that is lost. If I lost line of sight, then I want to move to line of sight, because what if the player keeps moving away? So I can put that in there as well. So if I don't have line of sight, I can go back. Right? That's something I can do if I don't have a line of sight. Once I'm in the sensing radius, chances are I'm not going to be outside of sensing radius. That's what it's going to be. But what about here? Can I be into close combat range? If I'm in close combat range, right, I want to do a close combat attack. But if I'm not, then maybe what I can also do is transition back, right, where I can say, okay, well, the player's moved away, move back to the player. That's also something that can happen. So I can transition back to here as well, right? So if the player moves away, move back, right? If the player moves out of line of sight, move back to line of sight, right? Radius isn't going to be lost, right? But I'm never going to go back to patrol state in this situation, because there is no arrow that takes me back. I meant move to line of sight. Going to close combat attack isn't needed though. Well, yeah, because move to line of sight, right? And then what if, as an example, right, I'm moving to line of sight and the close combat attack, they're within range. When I move to a line of sight node, right, Christian, I'm close enough to attack. Do I really want to move to the player? I'm already there. I don't have to do the move to player. I can just attack. So I can do that from here. That's what I'm saying. That's a case that might occur in our scenario. All right, so this is kind of something that is an exercise for you. Start thinking about plotting out what each of the decision matrices might look like, okay, as an example. So if you're going to use a state machine, plot it out, all right? If you're going to use a decision tree, plot that out. How would you make the decision tree work with, how can I convert this idea to a decision tree as opposed to a state machine? What would I do? How would I make this look different, as an example? Go back to that decision tree and start thinking about, do I have line of sight? If I have line of sight, as an example, that might be the first thing. Or if I don't have line of sight, do I have sensing radius? I might have one or the other. If I don't have either, then maybe stay in patrol, right? It's not be another way to do it. So let's see if we can, quickly redraw this thing, with the same thing, but with the decision tree, right? Let's see if we can do that quicker. So think about this way. If you're going to capture this as something that you might want to look at. But let's take a look at this in a different light. So let's make a new thing, and let's think about the decision tree at the top. So again, for the decision tree, I might have two things. Do I have line of sight? Yes or no, right? That might be the first thing that I care about. Line of sight, yes or no, right? And if I do, right, so if it's a yes, let's put another thing. If I do have line of sight, am I close to the player, right? So this is the next part. Am I close? So here's this one. So am I close, right? If I'm close combat attack, that might be the action. So that's the action that I would take, attack, right? So this is the tree now that we're thinking about, right? Because we're going to try and make the tree. The tree is going to have just nodes. So if I'm close, then attack. Okay, cool. What if I don't have line of sight? Okay, well, maybe I can see if the player's in radius. Can I detect the player in radius, right? If the player's in radius, if the player is in radius, what do I want to do? Move to line of sight. That might be the action. If the player is in radius, then the action would be to move to line of sight. So move to line of sight. When I say radius, that means we've detected the player. We've detected them. Okay, so that might be the thing that we want to do. Okay. And remember, the way that the tree would work is slightly different than this. So what if I'm close? If I'm not close, then I'm going to move to the player. Move to the player. Move close. That might be the thing that I would do, right? So let's do that. Move close. Right, so that's the line of action. And you can see where the action goes, right? The action always goes to the bottom of the tree, right? So this is where the action goes. And again, we're just basically, yeses are on the right, no's are on the left. Okay, no, I'm not line of sight. Do I have radius? Yes, move to line of sight. Sorry, this should be actually over here. This should be, if I'm in radius, yes, move to line of sight. If I don't have radius, what am I going to do? Patrol. So patrol. Which is an action we didn't talk about, because we say we start you off in patrol action, right? So this could be a decision tree. Would you agree? What do you think of this? Is this a decision tree that can be the same thing as the state machine that we just drew earlier? What are your thoughts? Looks like a tree, yeah, Jack. But I'm talking about, does this tree work like how it would work before, right? So again, every frame we go back and we sit there and say, do I have line of sight? Okay. So watch. So this is the update that the tree would do. The tree would go back every frame right? One thing to note is that the tree would go do one of these. It would come back, right, from whatever action it was taking. It would come back to this point right here, right? So once it's done doing its actions, it's going to come back and start off at line of sight again. Do I have line of sight? It's going to keep asking that question, every so often. Let's just put it that way, right? Because that's going to be the condition that's going to move it to whatever. Okay, so let's see. So let's start this off. So do I have line of sight? No. Are the player within the radius? No. Patrol. Okay, go back. Do I have line of sight now? No. Are the players in the radius? Yes, I've detected the player. Move to line of sight. Okay, cool. Do I have line of sight? Yes. Okay, am I close? No. Move closer to the player. Okay, let's go back out to here. Okay, do I have line of sight? I always check every single time. Yes. Okay, am I close to the player? Yes. Attack. That's how it would work. That's how a tree would work. And it would work differently than the state machine, because this one maintains state. It would keep on asking the question over and over again. Do we have line of sight? Do we have line of sight? Do we have line of sight? Now, again, this would promote a different set of behaviors in many ways. Even though the actions are the same, the way it would perform these actions are different. And really, I'm only asking 3 different questions. Do I have line of sight? Do I have radius? Or am I close? Okay. Questions around this now. What would you, now, did you change your mind? Did I make you change your mind between the state machine and the tree? Do you think the tree is easier now than the state machine? Would you still rather use the state machine? What are your thoughts? There's one condition here that we haven't met. What about if, the one thing that we haven't talked about is what happens if from any of these states is if I have low health. That is, again, what you can do is you can combine, kind of a hierarchical tree where I have 2 nodes, right? Where I'm in active service again, right? And we ask the question way above over here, which is, this is the active state. So I'm in the active, I go into active mode, right? I check to see if I'm in line of sight. Again, similar to what we did with the state. And then the other one would be, the question that I would ask at the top would be something like, is health low? Right? Is health low? And if my health is low, that would be the question at the top. Then the answer is, if it's not, then I would do this part, right? Because again, it's to the left of my question, right? So I would say, is health low? No. Then I'd be in active mode. Is health low? Yes. Then I would be in, a fleet. So we would be in inactive mode. This would be the thing, inactive, right? Inactive mode, let's just say. And then inside of inactive mode, I would take the flee action. That's all I would do. Yeah. So to me, right? To me, a tree structure, I look at it and it's just as easy to understand as a state machine. The idea here is, which one do you prefer to code? Which one is easier for you to translate into something that you can work with? That is the idea here. And we've only talked about 2 different structures. The last one we're going to talk about, which is next week, all things being equal, if we're all together next week. Next week, we'll talk about a behavior tree and how behavior trees are way different than what we've talked about so far. Okay, so that is that. Last things to leave you with. We talked about all these things, but the last thing I want to leave you with is what we're going to be doing in our lab this week. So in our lab this week, we're going to start with lab 6 as a part 1 as the starter. Okay, we're going to clean up the play scene. We're going to load our obstacle data this time from a text file. That's what we're going to do. Instead of having our obstacle data kind of be putting to obstacle 1, 2, 3, 4 like we did in the first part, we're going to load them from a text file. So it's going to give us more a dynamic way of loading obstacles into our scene, which is pretty cool. We're going to add line of sight information for each path node, as an example, to each of either the player, as an example, the target, or the spaceship, all right, or both. So the path nodes are going to be intelligent enough to know that they have line of sight. They're going to carry line of sight information for us. Okay, stuff that you're going to have to do this week as a student. So we're going to show you, we're going to set this up for you, and your job this week is you're going to draw a path between the ship and the target using one or more nodes, and you may use any tools and utilities provided. All right, and when we say one or more nodes, I want you to think about finding the nearest node with line of sight. So find the nearest node with line of sight to the player. Okay, and I just wanted to give you a preview of what this all might look like, okay, for tomorrow, for Thursday, right? So I wanted to do that. Alex is going to guide us through the first part, and he's put together a group of actions that we're going to take. But let's just kick off Visual Studio here just to give you a bit of a preview before we stop for the day, okay? So we're going to go in here, and let's run this thing and see what you're going to get. So this is the final version that you're going to build for tomorrow. All right, so let's take a look and see what this looks like. And this is great that I have this today. So what it's going to look like is we're going to go here, and this is these obstacles have been loaded from a file. You're going to toggle on the grid. Notice that the grid is going to have different colors. One part of the grid is red, right? And the other parts of the grid are green. And why? It's node line of sight to target. You're going to see that the node line of sight to target, these areas here, these nodes, right, in the graph, in this node graph, if you will, have no line of sight to the target because of the obstacles that are in here. Okay, that's how it works. I can also go node line of sight to the spaceship, and we've just used different colors here. So we have a blue color. We can see that all the blue nodes have line of sight with the spaceship. Okay, any blue node, you can draw a solid line from the blue node to the spaceship. That's the idea. If I can draw a line between the node to the spaceship with nothing else in between, I have line of sight. And I can also do, line of sight to both. So only these nodes here have line of sight to both the player and the spaceship, the target and the spaceship. Okay? That's how it looks like. So that's what we're going to be doing tomorrow as a bit of a brief. Great thing about that is it's dynamic. So if I was to go to node line of sight to target, and if I move the target around, let's suppose I move the target down here, notice it looks like almost like the target is casting a shadow. Remember, this is the great thing about ray casting, right? So think about the target as light, right? And it's lighting up all of these nodes, which is kind of a neat way of thinking about it, right? And you can see that any node that's lit up, that's where you can have line of sight between that node by drawing a direct straight line to the target, right? And as an example, and if we switch it around, and if I go nodes to spaceship again, I can move the spaceship around, so I can change the position of the spaceship. And as I move the spaceship around, you're going to see that some nodes are going to have, are going to gain line of sight. Other ones are going to lose them. So the ones that are red have no line of sight to the spaceship. And if I do both, which is kind of neat, it kind of changes because it has to have both line of sight to the spaceship and to the target. And these are the nodes, my friends. These are the nodes that you want to use as a hint in your exercise. I want to move to the node that has the closest node to the spaceship that has line of sight with the target. That is the exercise that you want. What's the closest node to the spaceship with line of sight to the target, right? So again, you can use node line of sight to target, right? So all of these would have all line of sight to the target, okay? So that's kind of the exercise for tomorrow. Okay, so that's kind of how it's going to look. Questions about anything we talked about today? I know we're kind of running a little bit longer than normal. All right, guys, if there's no questions, thank you so much. We'll see you guys on Thursday. Really, we're looking forward to getting this one done. I think it's going to be a great little lab, and it's going to set you up nicely for the stuff that's happening for you for assignment 3. Okay, thank you so much. We'll talk again on Thursday. I'll stop recording now on YouTube. All right, guys, thank you so much. Any questions?